last honor for me to introduce today's final speaker of our summer program. It's Dr. Vijay Reddi. Vijay is an associate professor at Harvard and runs the Edge Computing Lab at the Paulson School of Engineering and Applied Sciences. And just some background that's relevant to our fellows who are currently undergraduates right now. Vijay received his Bachelor of Science in Computer Engineering from Santa Clara back in 2003, then did a master's degree at Colorado in 2006, and a mere 4 years later, he defended his computer science PhD at Harvard with his dissertation entitled Software Assisted Hardware Reliability, Enabling Aggressive Timing Speculation Using Runtime Feedback from Hardware and Software. And while I have no idea what that means, I can see from the title that it is at that interesting juncture between hardware and software where things get quite interesting, which is kind of in the edge computing spot where we are right now. So you can tell that he's been kind of involved in this embedded space for quite some time now. In fact, he has over 42 publications and conference proceedings spanning from the computer architecture and robotics fields, and he has nearly 10,000 citations of his work on Google Scholar. So he's making quite an impact. So many of our teachers here know Vijay from his recent edX course on TinyML, and I just want to say that speaks a lot about his dedication to making edge computing sort of available to everyone. And he's worked with collaborators both within universities and within the tech industry to really try to democratize TinyML and to make it available to people around the world, regardless of their educational backgrounds or their economic status. And so we've been very lucky to be able to work with Vijay. I'm planning the summer program early on, and we look forward to working with him in the future on some new initiatives around edge computing. But without further ado, it is my pleasure to welcome Professor Vijay Reddi to give us a talk. And your talk is entitled 10
Commandments for TinyML.
The 10 Commandments of TinyML. Okay, perfect. I'll let you take it from here. I appreciate it.
Awesome. Thank you, Greg. Pleasure being here, folks. Thank you so much for having me. It's always exciting to talk to people who are excited about teaching others. All right, so I'm going to share my screen. So if you could let me know if it shows up, that'd be awesome.
We got it.
Cool. Yeah. All right, so in this talk, what I'm going to talk about is sort of like some general guiding principles, things that I've kind of picked up along the way in terms of doing really embedded machine learning. Obviously, I'm going to talk about it in the context of Tiny because you folks have really been dabbling around with stuff around the Tiny space. Now, so these are just personal opinions, but I feel like these are kind of based very strongly on things that I've gathered from not just me working in the space, but also being able to talk with a lot of industry folks. And so I only have about 10 slides, quite literally. So you'll have to interrupt me so we can stretch it out. I'm kidding. So with the 10 slides, for each one, what I intend to do is that I intend to go deeper into sort of giving you a perspective from how I'm looking at why something is actually important to look out for in the TinyML space. So feel free to interrupt me. I always enjoy answering questions. With that said, here are the top 10 TinyML commandments, I would say. I'm going to step through each and every single one of them. The 10 of them, and the way I kind of basically came across these is through the course that we talked about, through working with folks like Greg and just kind of thinking about what are the things that we need to do. And really, I would say I've kind of lumped them from the industry and academic sort of perspective in terms of how to think about ML, because the big thing that I found in ML is that a lot of us are very excited about it, but in terms of how we actually navigate that space, there's very little out there. You'll see a lot of courses, including ours, and a lot of books out there, but I feel like they often miss certain critical points. And the way I was kind of structuring this list was effectively trying to capture what are those extremely important things to look out for. And the reason I'm talking about these now is because you're sort of at that end of the program, and I'm hoping that as I mention these things, certain things will resonate with you, and then you'll be able to ask me questions, or so will Greg will, in order to facilitate that. So let's get started. The first and foremost one, right? The first one is really focused on the end-to-end ML workflow. What do I mean by the end-to-end ML workflow? Typically, most people will focus on the machine learning part, right? It's all the exciting part where we're trying to train a deep neural network, and what we want to do is feed in a bunch of data, and it produces some amount of output. But when you actually talk to a lot of the companies out there, like, especially folks like who are working at Google, Facebook, and so forth, one of the biggest problems they often find, independent of whether it's in the context of TinyML or embedded machine learning or edge ML or data center scale ML, the one recurring thing that everyone will point out is that a lot of folks working in the ML space often do not realize the importance of the complete workflow, which includes the prospect of just dealing with the data. Because typically when you and I are training our models, we magically have some data set that someone usually gives us. Now, from the stories that I've heard from Greg, in terms of things you all have been doing, you've actually been thinking about how to collect the data, which is really awesome. So I can dig a bit further into that later. But in addition to collecting the data, the next thing is obviously training the model. When we're obviously talking about embedded machine learning, there's a lot of nuance around thinking about this particular stage as well. I'll get into that. And then, of course, evaluating and optimizing it, and then finally being able to really push it out into an embedded device. Right? But these are all separate stages. By and large, the takeaway on this particular point is that we often focus very much on the yellow portion of it. And that, I would say, is sort of a very myopic view. And there's an increasing need to actually focus on the other parts, right? But that's
I'll just say that from our fellowship, we focus on the blue part for the majority of the weeks. Just try to get the yes.
That's actually great, right? Now, tidbit on this, I'm glad to hear that, because increasingly, I think we should really spend more of our time on the blue part, because the rest of the pipe we've gotten to a point in research and in the development process that's quite easy to be able to effectively train these models. It's not that hard to train the models. There are these fundamental building blocks that have gotten so mature that that's the easy part anyway. The hard part is really the data, because as you would know at this point, it's garbage in, garbage out, right? The model knows nothing. It's like if you have poor data, if it's biased towards one particular population or another particular population, however you define population, it's a fundamental problem. And no matter how good the rest of the pipe is, right? It's that data that turns out whether that rest of the pipe is actually useful or not.
I think we have a question over here from Sam.
Yeah. Can you hear me all right, Vijay?
Yeah.
Yeah, it's great to meet you. So one of the things I wanted to ask about in terms of the data portion of this is just how early on do you start thinking about making the way that you collect data in the early phases the same way that you'll collect data in the end implementation?
Yeah, how early? I think the first thing I would say is that we have to get into this process of just having a pseudocode for what are those requirements, right? Often, at least in practice, what I find is that whenever you're teaching computer science, what do? One of the first things we talk about is don't write the code. Don't think about the code first. Write the pseudocode first. And we try and get the algorithmic thought process in the head. Now, for data, I don't even think we have yet come up with the mechanism to kind of say, this is the pseudocode, this is the blueprint you need to come up with first. So I think, let alone collecting the data, I think knowing what you're collecting and why you're collecting the data, that systematic process, I think is far more important. Do you see what I'm saying, Sam?
No, I'm still a little bit confused actually on the distinction between how much attention to pay to whether or not the way you're collecting data at the beginning of your process is the same as collecting data at the end of your process. Can you maybe focus on that just a little bit?
That's a good question.
So when you say end of the process, what do you mean? Just so I understand that.
Yeah, so I mean in the final implementation. So when you are going to be collecting data and making inferences on that same data.
Gotcha. Okay. I think I get this now. Yeah. I don't think there's any one right or wrong answer here, right? I mean, both are equally important, right? I think the underlying thing is what are the requirements? I think the question is for me, it's a question of around the requirements, right? If you got the right requirements, and you know what data you're actually trying to collect, whether it's at the beginning or the later stage. And in practice, that's the biggest thing that at least I see, right?
Yeah.
They kind of step through it, maybe clear, but I appreciate the question. I think it's a good question. Cool. Yeah, so the next thing is around data engineering. Right? Now, I'm sure you've all heard about the term data science, right? It's all over. It's this next big thing that everyone wants to talk about all the time. Now, I just want to show this nice picture that I think kind of captures a key thing, which is like, traditionally we've been used to like software development, like someone writing a web app or a mobile app, right? Now, effectively, we jumped ahead on the data engineering thing, honestly, I think so, and then moved into like the data science. And everybody talks about data scientists are extremely important, okay? What do data scientists do? They look at the data, and out of that data, they try and come up with intelligent models, right? And then they go ahead and train the machine learning model. Now, one of the things that I often like to tell people is that be it an embedded ML or TinyML or any other ML, one of the big things that we're going to see is there's a real need for data engineers, actually, right? Because if you think about it, like when you have a data set that's already there, you never ask the question about where does the data actually come from. Okay? You often just take the data and then you try and do analysis on the data. But the question is like, who's actually producing that data? I like to harp on this point because data engineers are, I bet you, going to be the next big, highly sought out people. Because one of the fundamental problems that I think we have in the ecosystem today is that we tend to look at data sets as if it's a static thing, as if it's something you do once. Google does not go out and index all the information on the planet and create a ginormous hard disk and they don't throw up their hands and say, we're finished. What do? Why is Google so powerful? They're not powerful because they have the data. That is not the reason that they're so powerful. It's actually because they have a data engineering pipeline for search engines, right? The ability to continuously go procure data and then be able to extract the information, the needle in the haystack, in order to answer your question. Now, that is what is really powerful about search engines, right? Now, if you think about the context of ML, what do? It is extremely important. I'm sure we all are on board with that.
Yeah.
But when we look at the data, we tend to look at data as sort of like the static thing, like someone creates this data set, and then after that, we go up to the model. That is the absolute wrong way of thinking about data. And here's why. It's because what you really want to do is you want to build a data engineering pipeline. Just the way Google built a search engine architecture, they have an architecture that they know how to configure a request coming in, they know how to be able to intelligently mine all the information. Imagine if you're doing a TinyML device, like Hey Siri or something like that, right? You want to have some sort of keyword. What do we do today? What we typically do today is that some company somewhere goes out and hires someone to say, okay, I want a whole bunch of different, samples of Hey Siri, so that I can then try and train them on all my machines. Wait, not of course. That process of manually going and getting you or me or whoever else to actually contribute those audio clips is a manual and tedious process. That is not how we should be doing data sets. That is the most archaic way of seeing it, right? If we actually want everybody to be able to build intelligent models, and if it turns out that the data collection is the most important thing, then we need to figure out how we build a data engineering pipeline. What I mean by that, for example, in the TinyML kind of context, the keyword spotting example I just gave you, I want to be able to specify, for example, I want to say, you know what, I want to look at the words yes, no, up, down, and Yahoo. Like, these are the words I care about. And I want to get a model at the end of the day that's able to detect these keywords. Now, I should not have to manually go and get people to contribute samples for that individual data. Instead, what I need to have is, for example, a system that perhaps is tied to YouTube, is tied to movie channels, is tied to audio, podcasts, and all these different spoken and transcribed speech that is out there. And then you build a system that then goes and finds the yes, no, Yahoo, and whatever other keywords you want, and then generates a data set on the fly. And then from there, of course, now you have this curated data set, and then you can do the usual boring stuff, which is training the model. I really think that the interesting part is coming up with that engineering pipe. And a lot of people don't think about this. And I bet you over the next 5 to 10 years, this is really where we're going to spend most of our time, because I think we know the value of creating models. We know that they can create things. But we have come to the realization that it's not about model-centric design. It's really about data-centric design. So data engineering, I think, is going to become a very important field. I'll wrap this up by saying that just the way today you go to a school, you might actually have a data science program or a data science class. I bet you, if anything, we're going to have a data engineering curriculum.
Yeah, we have a question from the audience, but I just want to say, so you're talking like an IDE for data, like you would have an IDE for code that helps you, compile your code, an IDE that would allow you for our stuff, for like our electrophysiological stuff, that we just be able to use keywords that would be able to pull those sets in, that would be able to sort of find those in the needle in the haystack, so to speak, of ePhys.
Yeah, you shouldn't have to. You should be able to just automatically search for that data, right? Like, in fact, you don't search. You should just be able to say, this is the information I'm looking for. And the system generates the data sets on the fly. Just the way when you're searching, they don't have all the answers for you pre-labeled someplace, right? They intelligently try and figure out from the corpus of data that they have figured out algorithms that will then go and quickly grab all the right bits and generates that list we then use.
And Sid, you have a question? You can go ahead.
So it seems like the blue section is going to correspond heavily with data engineering, correct?
Mm-hmm.
So it seems like so if I'm understanding correctly, though, throughout machine learning and data science history, though, how much of an issue was having enough data or being able to create data sets an issue? Because from what I could tell, just having enough data seemed to always be an issue. So what do you think that before, for the very few data sets that we did have, they served their purposes well enough that we didn't need to focus on data expansion, but now that machine learning is being used for a variety of tasks for data that doesn't necessarily exist, we're now starting to realize the importance?
Said it perfectly, Sid. That's exactly the point, right? Like previously, when we had data sets like ImageNet, COCO, and all these other data sets that were created, those were good enough because we could take those and then we could try and figure out how to engineer these machine learning algorithms, right? So we were trying to figure out what the networks needed to look like. And we're reaching a certain level of maturity. There's still much more to do in that space, but we've reached a level of maturity that the technology there is actually applicable as is. But now we're starved for data. Because imagine, right? For example, you want to build a security system in an airport, right? Let's say you go train a model on ImageNet, right? Which is just basically mined information. Well, you might be thinking, well, does a data set have a gun in that thing, right? For example, yeah, I'm sure that ImageNet has pictures of guns in it because it's effectively mined from the web. And it's labeled as gun, and that's great. And your network will do just fine on that. But in reality, is that example actually useful? No one's going to be walking around holding a gun, waving a gun, and walking through the airport, right? It's going to be a concealed weapon. So what you need is a labeled data that actually looks like that concealed thing, right? Now, we have lots of movies that have that exact concept, right? For example, The question is, like, if we have the ability to do self-supervision there and then be able to automatically extract all of that data and create that data corpus on the fly, then I think we'll really start to unlock the capability. Guarantee you, in the next 5 to 10 years, data engineering is going to be the hottest thing. Doesn't matter whether it's embedded ML or just large-scale ML.
One final thing, though, on that note is so it seems like being able to build databases on the fly is the name of the game. But to do it autonomously, it feels as if you need machine learning to build the data sets for machine learning, which then feels like a circular thing. If you don't have the data set to identify it with, then at some point you're going to need some sort of manual input or human help assistance with getting it started before it does it on its own.
Like methods like active learning, for self-supervision, and so forth, I think are starting to become important. I mean, they've been important in the research community for about 4 or 5 years. And I think we're starting to see startups that are increasingly focusing on those sorts of technologies.
All right.
So, I mean, yeah, maybe at some point a human in the loop, right? Like, you can't get rid of the human. So I wouldn't say that, there's never going to be a case where humans don't need to look at this stuff today, right? I mean, even in Facebook and Google's, like, when they have all this data, you're still having people go in and curate it because of free speech and all these issues that you have, right? So I think humans are always going to be involved in that process.
One more question on this topic, if that's all right.
Yeah.
One of the things we sort of talked about with this same thing of like how to go about structuring the way we collect and store our data. How important do you think it is to have like an intuitive graphic user interface for doing something like this versus just leaving it sort of command line stuff.
I think there has to be some amount of intuitive way to visualize data, like having piecemeal plots or just being able to do dimensional reductions into embedding formats. Some amount of that, I think, is inevitable, because that's just the kind of stuff that I think you would get taught in a data engineering class, because you will know what the characteristics and quality of that data looks like. So I think those things are a bit inevitable, right? You have to have some amount of knowledge, and I think like that's where hopefully things like, if you've used Edge Impulse, did you all use Edge Impulse in the class? I can't remember, Greg mentioned, yeah. Okay, so when you use Edge Impulse, so I'm sure you must have done some of the dimensional reduction visualizations that they have, right? Which allows you to kind of see if there's actually a separation in the clusters of the data. I think you're going to see a lot more of those things coming out. I know of a whole bunch of startups, and if Pete Warden was here, Greg, to talk to you all? Yeah, Pete, as much as Pete is like, on the code side of things, building TensorFlow, Light Micro, and all those good things, he himself is actually, also very much a big proponent that like we need to see startups that are actually starting to build tooling for data visualization and data analysis. Not for just extreme data scientists, right? Just for average people like you and me who aren't specialized in data science specifically. Cool, let me keep going. The third point that I want to make is like, you got to realize that these systems are extremely complicated, right? And often I feel like in the embedded ML space, this becomes extremely important. Okay, what's the figure showing? Let's take this is a context of a typical TinyML sort of scenario, right? Often the data is coming in from a rich set of sensors. You have many different application tasks. You have lots of different data sets that you could potentially train on. You have many different models you could pick from. You have different frameworks that you could actually use to actually do the inference and run them through different graph formats, which actually impact the performance optimization you would actually get from your inference framework. And then you might have high performance libraries that match a given particular hardware. Right? And then you have a bunch of different OSs which have certain security policies and whatnot, right? And then you have a rich collection of microarchitecture at the bottom of the stack. And one of the things I think that's extremely crucial to realize is that when we're building these examples, I think one of the things we do is that we often focus on, hey, here's a certain deployment. But when you go back and you talk to people who are really trying to put something into a production use case, right, where they really care about it, the biggest thing that they struggle with is navigating this crazy cross-product across all these different layers, right? Which framework do I pick for a given platform? One of the most simplest questions that I often get from people is, I have this task. Which hardware do you think I should pick? This is a very simple question to answer when it is in the context of something like a laptop or something like a server system where you have a very homogeneous environment. Because a lot of things are fixed. In other words, you're probably running Windows or you're probably running Linux, right? And you sort of know what sort of compute capability you typically have, right, in these systems. And you have a single ISA. Embedded devices are notoriously fragmented. They're fragmented in the sense that every one of them might be running a custom OS, right? If they have an OS at all. Every one of them might actually need custom libraries. And these libraries, like CMSysNN, only works on ARM-based microcontrollers. Why? Because there's a software team that designs it because they know the exact ISA characteristics. But if you look at the amount of different embedded microcontrollers you have at the bottom of the stack, there are so many variants. There's so much variation at the architecture level. And that reason is because you want extreme efficiency in embedded systems. So you make it extremely specialized. The ISA is highly specialized. That's like saying like you and I are speaking the same language, but there's so many different dialects, which can actually present a problem, right? So because of that, what ends up happening in the ecosystem is that you have a lot of co-design that happens. And trying to navigate that space in a production scenario is extremely difficult. And a lot of us typically don't think about these things because we're just building experimental things and trying to understand some intellectual concept around, can I actually solve this problem using machine learning on an embedded device? And I think like it's when you shift from the research mindset to actually building a production pipe, that's when like the nuances show up. I can probably go about just this one point for a whole hour. The next thing is around metrics, right? So let's say you build some interesting application. Let's take a specific example, for instance. Yeah, okay, so let's go back to the keyword spotting example where I'm saying, hey Siri or okay Google or something. Sorry again. when you say one of these words, right? Now, I want to train a model on this, and that's a challenge that I give you. Now, if you're looking at it from the very traditional sense of doing machine learning, what is it that you're going to focus on? You probably open up a Google Colab, and then you probably train a model, right? Which means you're going to focus on, you have some data set that you got, then you're going to start training the model. And if you're training the model, one of the biggest things that we often do is that we actually end up looking at what's the trained accuracy of the model. Should you be doing that? Absolutely, you should be looking for accuracy of the model. But there's a big mismatch between what the accuracy of a model looks like on paper, quote unquote, as compared to what it would actually look like when you deploy it in a real system. If you hear in the background noise, that's my kid, so you'll have to bear with me a little bit. And where's that difference coming from? So think about it, right? If you're looking at things in isolation outside of the ML workflow, you focus very much on getting the most high-performing models. Now, this actually happens in the machine learning community, because when you write a NeurIPS paper or ICML or ICLR paper, what do we care about? Oh, we got to beat the state of the art. That's what we really care about. And so we try and push the accuracy. And one of the biggest problems that we are actually seeing in the real world today is the fact that a lot of these highly accurate models do not work well in production scenario. Because when you try and shrink that model, these algorithm people who are kind of not looking at the full stack, where they're just looking at some portion of, okay, I have some data, I have to have really high accuracy. They're not thinking about the consequences of deploying the model. So sometimes what you end up with are either the network that you have trained has complex operators that are usually not supported well on the underlying hardware, especially in embedded hardware. You might not be able to run all the operators well, right? Because you're just training it on a large-scale system, and you're hoping that when you deploy it, it works well. This, believe it or not, actually happens in production. In fact, like I work with Pete Warden and his TensorFlow team, and we see this all the time. But production use cases where they come in and say, well, this is not gonna, like, they want to deploy this model. Well, by the time we actually put it on the device, we're like, sorry, no can do. The use case won't fly because it doesn't work efficiently at the deployment time. Now, talking about the metrics specifically, I said you look at accuracy, you want to push the accuracy high. Now think about this. Let's say you're building, an Alexa device, and you want it to obviously respond accurately when you say, hey, Alexa. From a pure accuracy standpoint, it makes perfect sense to try and get the most accurate model. But the thing that you often do not realize is that when you deploy it into production, what you're actually interested in is what's the latency. So there's a very critical trade-off between the accuracy of the model and what the latency is. You typically want the latency to be really low, really slow, because you can have a highly accurate model that is 99.9% accurate, but will you be happy if it takes about 3 to 4 seconds to wake up, right? So that's like me saying, Alexa. Yes, Vijay. Well, that's pretty annoying because that's not an interactive device, right? So you really have to understand. So what that means is that when you're training the model, the metric really cannot just purely be the accuracy of the network. It actually has to be some sort of accuracy that's coupled with some sort of latency. This then might not seem like rocket science when you just kind of talk about it, but if you look at where the field is, by and large, the machine learning folks tend to just focus only on accuracy. I can tell you because just today, for instance, they rejected one of our workshop proposals, which is coming from ML Systems. It's a systems community that we have, which talks about how do we actually make sure that we're building systems that are efficient, both in terms of accuracy as well as latency. And it's a huge industry consortium today. And yet, when we're trying to penetrate the machine learning community, it's very, very hard to get this concept across. Now, if I put this in a practical perspective, like in a big company, what you end up finding is that there's no one person doing the end-to-end pipe. So what this means is that typically there are machine learning architects who are building the model, and then they toss it overboard across the wall, and they hope that these deployment engineers can somehow magically put that model, which you then cannot change at that point because the accuracy is achieved by that model. So this presents a serious problem in terms of if you don't understand the right metrics. I would much rather have an Alexa model that responds much more efficiently with a slightly lower accuracy, right? And this sort of a trade-off is, again, something that you will never see unless you get into the fundamental role of deploying things onto device. Which
I would say that the edge
is
impulse
extremely important to put things onto real devices. Now, you folks have obviously been doing this, right?
Yeah, I was going to say the edge impulse has a. It tells you. Oh, sorry, am I muted? Can you hear me
We
now?
can hear you, Greg.
You can't hear me? Okay. Now, I was just saying that the edge impulse does tell you when you build your model. No one can hear me?
No, we can hear you. I think he can't hear us.
Oh, he can't hear us. Oh, I gotcha.
Can you hear us, Vijay? Vijay,
do you hear us? We know you don't hear Greg, but do you hear us?
No, he lost all of us.
Okay.
Oh, no.
No worries.
Can anyone hear me?
Yes.
Yes, I can.
Hear me. Okay. That's odds. Okay, so this must be on my end.
Yeah, Greg can hear us.
Oh, but
Greg
I
can hear us
need to
too.
be able to hear you though. That's fine. I'm sure you can hear my kid in the background.
Yeah.
Here, let me just reconnect. Hopefully that works.
Okay.
Greg, do you have an auto cap thing on every time you type no? Or is that just a habit? No! In 2 caps. He did it twice.
I think it's just me.
He just does it unnaturally. Just get the data.
I didn't notice that was a trend.
No, it's not enough. Gotta put the oomph.
I'm yelling it every time.
But it's positive, that one. No worries.
No, but it's funny because we did have that discussion. We were always looking at that inference time in edge impulse, and so that, because in the back of our minds, we were always thinking about what is this going to look like in the real world when we actually deploy these things. How quickly, how many times per second can we to do that? So anyway, it's good to hear that, and I wish they would make that more of a prominent thing, right? They should put that right in with the percent corrects on the training set, testing set, and then the inference time being promoted, so to speak.
Yeah, it's kind of validating to hear, even though this is the first time you guys are doing like a TinyML thing, that you're focusing on all the right stuff. Just kind of nice. Nice little pat on the back.
I think it's a Vijay joined the group, but
Maybe someone has to let him in.
We lost our speaker.
No.
Oh, he's not coming out. He's back.
just joined, but
We miss you, Vijay.
Okay.
That part. That's the most important part.
Can you hear us
Okay,
again? Or no?
perfect. Can you hear us again?
Yep.
No, I was just mentioning that we always would have discussions on the edge impulse of, it would tell you the inference time that it would take for you to run that, and we were kind of optimizing that one because we kept thinking in the back of our minds, like, what is this going to look like when we actually go to deploy it? And so we were, and some of them would be much longer than others, but I didn't quite have an intuition yet of what makes that thing go down. Is it just the complexity of the layers, the number of nodes per layer, or is it a combination of the both?
It's really a combination, right? Because that's what I'm saying. Like, what a lot of people often don't realize is that when you actually push it down to the device, you go through a different pipe when you actually compile the network down. And whether, for example, in this stack here, if you're using an ARM microcontroller, which is probably the ones that you folks are dealing with, right? Then whether you have enabled CMSysNN or not, functionality-wise, it is ditto, right? Functionality-wise, it will work out of the box, but the performance is going to vary quite dramatically whether you have actually enabled CMSysNN compiler and whether CMSys actually supports the actual underlying microarchitecture. Right? And those kinds of things actually don't get captured effectively, and that's why the estimates tend to usually be off, and that's where transparency becomes extremely important. All right, so where was I? Yeah. So it's talking about deployments, right? So there's an example where, for example, if you don't understand what the characteristics of the actual target microcontroller are and you're not physically deploying and you're not physically evaluating it on device, then you've got a problem, okay? Because what you think is going to happen is not what ends up happening on the embedded device. So, all right, the next thing is sort of like when you're talking about reproducibility, right? Number 6. So in terms of reproducibility, one of the biggest problems in the machine learning space, by and large, is whether you can actually faithfully reproduce the execution characteristics that one person experiences on a single system on another system, right? Because you might say, for example, you might have two pieces of hardware. So, for example, like, let's just pick on the Arduino Nano 33 BLE, right? This device might have capability X. Another embedded device might have capability Y. Now, if let's say you are just someone who needs a piece of hardware and is trying to make a product, and you're trying to decide whether should I get the Arduino 33 or should I get this product's XYZ. Well, how do you evaluate this? Now, when you're looking at machine learning systems, it gets extremely complicated because of this vertical stack that I was talking about earlier. It's hard to reproduce a number. So imagine someone, let's say Arduino comes out and says, okay, you can get this kind of performance on my device, so you should buy my device because it's going to meet your latency requirement. Well, someone else might say, oh yeah, my model also totally meets that requirement. But then you go into the details of did you quantize the model? Like what precision, what numerical systems are you talking about? Are you talking about doing your neural network processing in integer arithmetic, or are you talking about doing it in floating point arithmetic, right? So by and large, typically on embedded devices, you want to do all the arithmetic using integer, because from a microarchitecture standpoint, it's very simple to implement, it's extremely low power, and it works well. The only problem is that when you take a machine learning model and you quantize it down with integer arithmetic, you end up compromising the accuracy automatically, because all your floating point values now get rounded off to some other integer value. Yeah, that's okay. But then it's like you need to know that sort of a nuance or a fact, because if you don't know that nuance, then the problem you're going to have is that you might end up choosing this integer arithmetic-based microcontroller seems really good. And if you did not know about the quantization effect, then you would end up choosing that device, which automatically leads you to a crappier performance. It might look great in terms of your latency, but the model's accuracy that you thought was going to be certain value is now going to drop. And if it drops, well, then maybe it's a dead use case, because at that point, it's continuously waking up and saying, how can I help you? How can I help you? Right? So you might have false positives, or worse, you might have false negatives. In the case, if it's in an autonomous, let's say in an autonomous car that has a smart sensor inside its tire, and it's supposed to alert you if something is wrong with the tire. Well, if it's a false negative, saying like, well, it basically ended up not detecting the failure, well, you might just crash and die. That's a pretty bad scenario. Right? So you really need to kind of get into the nuances of being able to actually reproduce. And so, one of the things that we had built out was this benchmark, which effectively outlines the precise rules you need to have in order to be able to faithfully reproduce results across any two systems, so that you and I, as average people, can actually look at those numbers and be like, okay, for this particular task, be it like image segmentation or image classification, I can know that, okay, the two numbers that I'm looking at are actually comparable. And if they're not comparable, there are not footnotes in there to help me understand why they're not comparable. Seems like such a simple thing to do, right? How can comparing two systems be so complicated in a day and age where we're building all these complicated machineries for these things? You got to remember that we're still in the dark ages of building machine learning systems. The best analogy I can give you is like, I often think of it as like, if you want to build a machine learning system, you're going to the blacksmith who knows exactly how to do this, and there aren't that many of them around, right? They're experts, they're domain specialists, and they know how to build machine learning systems. Now, fast forward by, a couple of centuries, and what do you end up with? You end up with the Ford sort of, assembly line, right? Where we rubber stamp vehicles with extreme precision, and then everybody is able to easily get the benefits at scale. We're not in that place, right? We're still in the age where, for example, like when the Wright brothers age, where they're trying to figure out how do we build this airplane and then get it off the ground for a little while. We're not in a point where we have, Boeing and Airbus building out these 747s and 777s, and then everybody just blindly buys them and knows how to operate them. Might seem a little extreme, but I kid you not, we are by no means as advanced in terms of making this sort of technology globally accessible.
It's awesome. That's exciting, man. I love that. That's cool.
Yeah, I think it's a very exciting time, not from just being able to use it, but actually being able to shape what this engine is going to look like, right? So there's a lot of work going on. I encourage you, specifically if you're interested in these kinds of things, you want to really understand what's the nuance and trickiness behind it. There's this paper that we just submitted we submitted a while back on ML Part of Tiny, which explains what are some of the technical challenges in being able to reproduce numbers on any two systems precisely. And there's almost a science right now of trying to understand these things. The next point I want to emphasize on is like, let's not just kind of completely forget about machine learning, right? So for example, this is bullet number 7. What do I mean? I've been talking about machine learning. It clearly says TinyML in the title. Well, okay, well, when I'm using machine learning, largely I'm talking about deep learning. Specifically, what is deep learning dealing with, right? Deep learning is dealing with a lot of data. It's all about big data. If you have a large corpus of data, well, that is awesome, because then you can try and train these models to detect patterns and then be able to do inferences on it. But you're not always going to have lots of data. That's the truth. Often, especially in the embedded or TinyML space, you have machine learning, which is more of a statistical-based methods, right? Where you're looking at decision trees and those kinds of example algorithms, which are very simple. So there's this lesson, right, which is like everybody right now is very excited about deep learning, which is computationally expensive. Well, it is also sexy, so everybody wants to stick on it and say like, yes, even my rice cooker says it has AI. I don't know what AI it's actually doing for cooking rice, but apparently it has AI technology inside. I bet you all it's really got is just machine learning. It just knows, oh, temperature's a little high. These are simple decision trees, the algorithms that you can actually look at it with a little bit of data. You can actually do very intelligent things. Why do I care about this? Well, for one, the big thing is that I don't need a lot of very complex arithmetic to actually happen. Running a deep learning model with all the gem calculations, the matrix multiplications that are happening at the lowest level of the hardware are extremely costly in terms of energy. And they will drain out a TinyML system's battery before you know it. So therefore, using simple machine learning algorithms on embedded devices is actually remarkably useful. So I always like to tell people, don't just immediately throw a neural network just because you have a microcontroller that's capable of running neural networks today. It might very well be the case that you just want to use very simple machine learning algorithms to actually do the task. And I think this is actually a very important thing because the efficiency argument is so critical, and often, unlike traditional bigger systems where you have to run a whole bunch of tasks, machine learning on embedded systems is particularly unique because you're often designing that device to perform one task. Rarely do you have a TinyML device that is going to do 10 different tasks. We're not at that point. We're likely not going to be at that point because it's all about efficiency and running on coin cell kind of battery scenarios, right? So you got to keep that in mind. Now, I'm going to take a step back from like talking about all the technical things and try and talk more generally at sort of like how to kind of move about in this space. I'm trying to pull us all back up. So one of the things I like to say is like, don't ignore what the industry is doing. Often what I end up finding is that a lot of people get very excited about this and they often forget what are the real industrial needs, and they come up with all kinds of interesting use cases which seem really cute, but in practice will actually not go anywhere. Now, this is great from a pedagogical perspective, meaning, as teachers, that's our job. Our job is to always ask questions and see if there are new answers we can find. But if we're trying to build products, you will find I have people that often come to me and ask like, oh, I have this idea and I want to do this. And I'm like, I have no idea why you want to do this because I don't see any need in the industry in the practical scenario. And often people also forget what are the actual requirements of an industrial deployment of a TinyML device. For example, over-the-air updates. How do you actually update a model that you've already deployed in the field? How do you actually get to think about like the over-the-air updates? Because whenever you open the comms channel, you're going to burn up energy. So how do you systematically think about doing over-the-air updates when you deploy things into production? I was helping a company, and one of the biggest mistakes that they had made when they had deployed their TinyML deployment was that they only focused. They got sold on the idea of like the efficiency of a single node. What they didn't realize was how you need to think about false positives at scale. So they had over 1,000 of these nodes scattered. Now you got to think about this. They're using it for security system, but then the false positive rates have to be that much lower, right? It has to be a very, very accurate model, because if it's 1,000 of those nodes, any one of them effectively mispredicting, turns out like a lot of them are continuously mispredicting, just the sample size, right? So you need to think about what ends up happening when you're actually doing a practical industrial deployment where you actually have to manage multiple TinyML devices, not just a single one of them. Then, of course, I think there's a great opportunity like around the TinyML community that where people are trying to learn and grow. I'm obviously a big fan of building community around this kind of a topic because I think it makes learning and building things much more accessible because you can actually get people excited to collaborate with one another. To be very specific, for example, recently we ran a workshop for the Navajo community where we're introducing them to just machine learning and then using TinyML, and specifically they use the Navajo language to actually train a custom keyword spotting model that wakes up for a word that is trained in their language, which is Yate. And what's particularly interesting is that like these communities don't have data sets. They don't have a speech data set for themselves, right? Think about the last time when you were talking to your machine. When was the last time you spoke in some other language outside of English to an intelligent device? It's always, hey Siri, do something, right? It's always this, all the speech recognition technology is not in our native. I speak Telugu with my parents. No chance these machines know how to interpret a word in Telugu, right? But the language is an extremely, it's an extremely interesting thing, right? I bet in a few years we're not going to be touching devices. I'm almost sure that my daughter, who's 5 years old, is never going to touch a screen in like another 5 years because it's just going to be spoken interfaces, right? Your remote, you don't need to push things. That's so archaic, right? It's just the way she doesn't understand that we actually used to have a phone that was tethered. She just doesn't get the concept. She's like, why would you want to ever build something like that? That's what she asks me. Because she's like, you just use a smartphone. You just walk around with the phone, right? So if you can train these devices to actually be intelligent, where you can collect data across different groups. You have to localize this because it's around speech, for example, right? Then in the Navajo community, for instance, we have teachers who are then working with their students to collect small samples of data, like little bit of data into the Edge Impulse pool. But then collectively, when you run a competition at the end of it, where we get these different schools to actually compete with one another on their keyword spotting model, what's beautiful about this idea is that like it gets the local students and the teachers who actually interact with their elders to try and capture and save that language in a way, right? And by collecting the data, they're actually having to interact socially with the elders, which creates this bond. And then they're collecting the data, and that data then becomes, you can pool all of that data together to effectively create a data set, right? And you can use that data set then to kind of actually make it a community resource, right? And so the point I'm trying to circle back with the community community point here is that you can actually use the embedded ML devices because they're so personalized to us. It's not like you're just saying train to detect a cat versus a dog and then just do it in the cloud when you're learning. It's actually a great opportunity to build community by using technology to solve an interesting problem. Then, of course, finally, I like to say, like, let's not ignore the needs of society. Like, technology is always cool, but we should always build technology because we're excited about solving some interesting problems. And I think TinyML is like kind of crazy because it's one of those technologies where you don't need extremely sophisticated things like machinery and a lot of money and so forth to build some things. An example here is like, Saving the Elephants project, right? Which is you're trying to just build intelligent sensors that you can tether to these animals so you can then use that information to intelligently learn about either how they're communicating with each other. You can't follow these elephants day in, day out in Africa or someplace, right? So you can't strap a ginormous computer onto their back. That's not going to work. But if you have TinyML devices that are trained with these machine learning capabilities that can pick up intelligent points, then they can transmit that data back to an edge server, which can then kind of, notify us if there's something going on. For example, if there's a poacher around them, getting the officers notified would be helpful. The point that I'm trying to get to is that I think like TinyML enables a lot of social good applications, and I think that's really where the momentum has got to be. There's obviously interesting consumer end applications that we can build. Companies will go out and build that. But if I was a teacher, which I am, one of the things that I often try and get my students to do is like really think about these kinds of applications, because I think they're much more engaging, and I think it lights the fire for a lot of people. Now, I've talked a lot about these principles. I'm very passionate about like being able to give access to machine learning, especially this sort of, extremely powerful technology has to be globally accessible for everybody. If we think that today's world has got a divide in terms of like, what people know in certain countries and have all this technology, in certain other countries, I think if we don't get them to understand the value of their data, it's more than likely that we're going to create a whole new sort of AI divide or digital divide. It's just going to basically get worse. And it falls on people like us who are learning about these things to be able to give it back to the community and help them all grow. They might not necessarily need to know how to do machine learning, because that's a pretty big step function, but they sure can understand the value of data. And tying this back to machine learning, right? If you don't have data, you don't have machine learning. So if you can control, or you can teach people to understand the value of their data, then I think you can even take communities that are struggling and empower them, because people want to be able to provide service. And if they know what their value of their data is, and then they can then use it to do intelligent things, right? So we put together this this course that Greg mentioned, this edX course, and what this document specifically goes through is sort of trying to get people to understand why we did the course and what's the lens through which we looked at how to do a course, and how do we teach TinyML in a certain way that it actually has wide applicability over a large set of people, not just people in some set of schools, for instance, right? So I'm extremely passionate about this. So if folks have any questions around this, I'm always happy to talk. With that, I'd like to stop talking by saying, like, the future of machine learning is tiny and bright, and hopefully you sense how crazy I am about this. I'm happy to take any questions.
Awesome. Well, we have time for a few more questions. Anyone have any questions from the audience here? And then we've taped this, Vijay. We're going to be able to play it back. Some of our teachers are still in other commitments right now. They'll be following it tonight. So cool.
Will this be available for, or is it just going to be recorded for posterity somewhere?
Yeah, no, this is going to be reported. We have a YouTube channel where we're putting all of our keynotes on there. So
okay, cool,
excellent. Okay, go ahead.
Hi, Vijay. Nice to meet you. I really enjoyed the talk. My question would be, just as someone who's really involved in the field, is there anything that you're personally really excited for about ML in the next 10 years? Is it the data processing? Is it, like, I don't know, generative models? Everyone seems to think something new is really cool. So I want to see what you think.
It's data. Data is king, right? And I want us to be in a world where we have search engines for machine learning tasks. This notion of collecting data, and I almost think that the government sometimes with their funding, the way they're thinking about the funding model to support machine learning, where they say, like, oh, we need lots of data sets. I'm like, you have it wrong. In my head, I strongly believe they have it wrong, because what we're going to create is a bunch of those old static pages. You know what I'm talking about on the internet? I don't know if you ever remember, there are all these dead weight pages that just stick around, and then Google and Microsoft and all these search engines need to figure out, how do I actually cut that out, because it's all just noise. It doesn't have up-to-date information. So how do you actually get the right information, right? And I think for that, you need to focus more on sort of these data engineering principles. If anything, the one thing I'd say, around this space, I'd be super excited about cooking is, what does a field of data engineering look like? If we were to teach data engineering in universities and classes, what does that really look like? Just the way data science. We know what it means to have data science as a minor, almost a major in certain universities, right? So I'm very interested in defining what data engineering is. And it's not just me. There are a couple of us actually trying to put together course materials and trying to bring some of the best minds together to help kind of chart out what that map really looks like. What does a field of data engineering do? Because we are doing it today, but it's just this information that's kind of caught up in people's heads.
Very cool. Thank you.
Thanks.
All right, I'll ask one. The latest model trends right now are these attention-based models. How much longer until we get attention-based models in TinyML?
Oh, attention-based tiny models. In fact, there's a paper that just came out for attention-based networks and keyword spotting from ARM. I think this just came out last month.
Wow. Okay. So that's already happening. Okay.
The tiny transformer is sort of a network that sits on a microcontroller, and it does keyword spotting, and it knocks the pants off the thing. It's amazingly good. So I'm curious, since you all have been asking me questions, I'll flip the table around. What's been the most hardest or most insightful thing about this experience around this workshop around embedded ML?
Hey, students, you guys want to take that one?
I think mine is very direct. It's just like you said in the presentation, the practicality of implementation versus just wanting to make the best model, the cleanest model. Before this workshop, I was definitely someone throwing the model over the wall, and now I had to receive it, and it sucked. So it was pretty cool to see the process front to back. So I've definitely learned a commandment from this, I think.
Yeah, what's super interesting about TinyML, right? We all had this problem, but it's just that the resources and so forth were so large that you could almost mask that capability without having to get the model engineers to actually recognize these things. And that's what I love about TinyML, because that entire process, that complex process, is something you can witness firsthand. And it allows us to reinforce that key goal of the industry sees a really dire need for full stack developer experience. Right.
Absolutely, doing the whole process and like being like a mini full stack TinyML.
Exactly.
It was great.
From my perspective, something that I wasn't quite aware of when we first started was that importance of that connecting where the rubber hits the road at the end, where the sensors are going to be going directly into the microcontroller, versus the planning portion of it, which is kind of more in the Python world. And so we were doing things, manipulating the data in Python to get it to look, we were doing the kind of the Wizard of Oz. We can kind of see one versus the other. And we got pretty good at being able to do that. But then when we go to deploy it, the slight differences in how our filtering works in Python versus how it works in C running on the microcontroller made to have a huge effect. And so, so we've learned a lesson that we have to be more careful when we collect the data for training, that we're actually using the actual thing, not a close enough thing so I think we have to build better toolboxes on our end so that we can at least handle our domain specific data structures, which are these basically serial lines of data. So
actually, that makes a really interesting point. It's kind of jumped out. Is that, like, talking about sensors and this data, we don't have like the ImageNet for sensors. Okay? And if you work in the ML space, ImageNet is this classic ginormous data set that everybody gets exposed to at some point or the other, right? But in the TinyML context, it's really not about the processing, that's not what it is, right? It's all about the sensors. And one of the biggest problems that the industry is seeing right now is, like, as much as we're all excited about this, if we really want to crack this, though, you need the data, and we don't have large corpuses of sensor data to actually be able to build useful applications in practice. There's a lot of data there, but it's not necessarily data that you can rely on.
Yeah, we've been kicking around that idea that we actually are in a pretty unique spot because we have kind of this public-facing company of citizen scientists recording these data, right? So we could actually have a repository of EKGs and EEGs and alpha waves and these different types of stuff that data scientists could use that to be able to make things in the future. So it's and I saw that you have some initiatives around that, sort of building these public data structures and data sets and stuff like that. So that maybe we can
we've been kicking around this idea about, like, maybe creating a data commons, where the intent is, like, when you have these different sensors, it's not about just having the data, right? The next thing becomes, how do you ingest the data? Because you want that data ingestion process to also be nice and clean, so you can easily throw different kinds of sensor input data streams to the system without having to read a whole bunch of middleware piping in order to get the data in, right? And how do you standardize across different types of sensors that have very different kinds of characteristics? The IoT space has kind of tackled some of this, but it needs some bit of changes, or have to come up with a whole new system. But something like that could benefit, is what the industry largely says.
Absolutely. Okay, it's getting to be 4 o'clock, so I just want to thank Vijay again for taking his time out of his busy schedule to come talk to us, and I do appreciate that. So, we have 1 more, or maybe 2 more days left of our summer fellowship, and so we're going to be posting our posters online soon, and we're going to hopefully have some videos to share with the final product. So, anyway, thank you guys so much.
Awesome, thank you, folks.
Vijay, I think there might be another comment or two if you have a moment to stick around.
Sure.
Yeah.
I got you.
Yeah, I think especially for our projects, unfortunately, we didn't get to that point, but I was very curious from the beginning what the difference might be between like personalized and like more generalized models, like using the same kind of data but from different people, and how the model actually then changes if you want to like train the device personalized or then have like the generalized version, or whether the generalized version is actually possible, or the sense might not be like powerful enough like the Arduino to actually do the computation. We didn't get to that point, but I'm still kind of really curious about what the differences are.
That's a good question. I don't have a direct answer in terms of just the sensor, the particular sensor kind of thing. But if we just take, for example, a microphone as an example input, right? And then you're dealing with different kinds of data, right? So let's say we're training a keyword spotting model. And what do we typically do, right? Like generally what we do is we end up collecting a whole bunch of data for the set of keywords that we're interested in, and then we train a model. Now, if I go to a different language, what am I going to do? I'm going to basically repeat that exact same methodology of hiring a whole bunch of people, or you and me sitting there recording whatever word a billion times, right? Well, let me show you on the slide. So there is this paper that we just recently published. Shot word spotting. So this is a paper that is coming out in Interspeech. I have a video for this for my students. And basically what we show is there's a few-shot keyword spotting in any language. In other words, rather than manually collecting like these 1,000 samples and then training it for English and, you know, Turkish or any other favorite language that you want, right? What we basically show is that if you can create a generalized embedding representation, which I'm showing you here in the middle, in the yellow box, that generalized embedding representation can be, on the right-hand side, retrained effectively very quickly with just 5 examples. In fact, it can actually be done with 3 examples, right? Of me just saying, like, let's say I say namaste, 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 and then the model automatically knows that it's that word. So instead of having to collect, like, for example, I don't know if Pete mentioned this, but, you know, he has about 2,500 samples for each word on average, right? Instead of having that, here we're saying that we create a generalized contextual embedding representation, and this embedding representation can then be very quickly, with 3 examples, pick up the words that you want, right? Which is remarkably fast, and it's extremely important in the context of low resource languages. I'm talking about, let's say, you know, you want to deploy something in some rural part of India, right, in a village or something where you don't have these nice data sets and so forth. Like, it's extremely hard to kind of go and build these data sets. So backtracking this up to your question, the thing that I'm trying to get to is that this notion of building these generalized embedding representations is starting to drive in the research field, at least, because they're finding that, you don't have to have lots of data. I mean, initially you have lots of data, but then you come up with this embedding representation that maybe someone with the ninja chops can come up with the embedding representation, but then others would be able to quickly take this embedding representation and just be able to quickly fine-tune it for their particular deployment scenario. Maybe it's for a slightly different microphone sampling rate, or maybe it's a slightly different pressure sensor with certain other characteristics. Do you see what I'm saying? But this is something that I think we're going to see more and more of, because it gives the ability to generalize into tasks. Now, whether this can be done across sensors, that I don't know. I've not thought about it. But at least within the context of sensors, you can do this. Links for these kind of things. These are obviously, you know, research-related things.
Well, is that all? Thank you very much again. Thanks for sticking around. That was awesome.
Yeah.
Thank you. Thank you again, Vijay.
Bye.
Greg.
Woo!
Great.
Thank you.